Hello, and welcome to my next video for my Capstone project. I don't know if you can tell, but I switched my camera. I stole my mom's phone, some Chinese phone, and the camera's much nicer, so I'm going to use that now. Anyways, today we're going over the second part of acids and bases, specifically salts this time. So let's get started. Let's get started with what a salt really is. A salt is a compound that consists of a cation, so a positive ion, and an anion, which is a negative ion. Some common examples are like NaCl, that consists of Na plus and Cl minus, or KBr, which consists of K plus and Br minus. And these are just common examples of salts. Now sometimes when you take these salts and you put them in water, they're going to dissociate, right, into its ions. So for example, if you threw some table salt into water, it would dissociate into your Na plus and your Cl minus ions. And what happens is sometimes these ions, they're going to react with water and they're going to form either an acid or a base. So that's what we're going to be mainly focusing on for this video. How do we know if an ion is going to form an acidic or a basic solution? Or maybe it won't react at all and it'll form a neutral solution. So let's find out. We'll start with cations, so positive ions. The thing is, most positive ions actually don't hydrolyze. That's what we call it. Hydrolyze is when the ions react with water and then they form acid and base and all that. So most positive ions, they don't react with water. So usually they do nothing. Of course, there are 4 exceptions, which Mr. Cheung likes to call the Fab 4. And what these are Al, H2O, 6, 3+, but you can mainly just look at the Al3+. You have iron, H2O, 6, 3+, or just iron 3+. Same with aluminum. You have Cr, H2O, 6, 3+, or just Cr 3+. And finally, you have ammonium, NH4+. So these 4 are the only cations that will hydrolyze. And when these cations hydrolyze, they're going to form an acid. For example, let's say we had an ammonium ion. It's going to react with water. And that's going to form our ammonia and hydronium. And that's why it's going to be acidic. Now let's look at negative ions, or anions. The thing with anions is that almost all of them do hydrolyze to form a basic solution. So it's easier to memorize the few that don't hydrolyze at all, or don't hydrolyze to form a basic solution. And what Mr. Cheung calls it is the silly 6. Because there are 6 of them, and they are silly because they're unable to hydrolyze. And these are ClO4 minus, I minus, Br minus, Cl minus, NO3 minus, and HSO4 minus. Now these are actually basically just the conjugate bases of all your strong acids. You'll see that at the top of your acid and base relative strength table, whatever that's called. I'll put a picture there. The only exception is that HSO4, it is a silly 6 because it doesn't hydrolyze to form a basic solution, but actually forms an acidic solution. Because you can see there's still one more H there, and that could be donated to form hydronium. To recap, when you have a salt, which consists of a cation and an anion, when you throw it in water, it's going to dissociate into its ions, right? And then now you have to look at these two ions. And you gotta think to yourself, will it hydrolyze and form an acid or a base? So that's the first step. Alright, now with what we learned, let's look at 5 different scenarios. So first, scenario number 1. Let's try to determine if NH4Br is forming an acidic or a basic solution when placed in water. First off, we know that NH4Br is going to dissociate into our NH4 plus and our Br minus ions when we place it in water. Now we have to ask ourselves, is the cation a Fab4 and is the anion a Silly6? We know that NH4, that's a Fab4, right? So it will hydrolyze. And as for our Br minus, that is one of our Silly6. So that means it will not hydrolyze. So in this case, our Br minus is going to be a spectator ion. So it does nothing. So all that's happening is our NH4 plus is going to react with water. And that's going to form our NH3 and our hydronium. And because there's hydronium, this is going to form an acidic solution. And that's our first scenario, where our cation will hydrolyze and our anion will not. Let's look at our second scenario here. This time we have MgF2, and we're placing in water, and same thing, we're trying to determine if it's going to be acidic or basic or neutral. First, we have to write our dissociation. It's going to dissociate into Mg2 plus and 2F minus. Now we look at our cation first. Our Mg2 plus, that is not one of the Fab4s. That means it's not going to hydrolyze. Now we look at our F minus. The F minus is not one of the Silly6. That means it will hydrolyze. And our Mg2 plus in this case is the spectator ion. And what we have is F minus reacting with water to form HF and OH minus. And because of the OH minus, it's going to form a basic solution. So that's pretty easy, right? We just look at our ions, check if they hydrolyze or not, and then see if they'll form acidic or basic. But now let's look at, what if they both hydrolyze? Then how do we know if it's going to be acidic or basic or neutral? For example, let's look at NH4F. That's going to dissociate into NH4 plus and F minus. Our NH4 plus is part of our Fab4, so it's going to hydrolyze. Our F minus is not a Silly6, so it's also going to hydrolyze. And now we have two separate reactions happening at the same time. Our first one is our NH4 plus reacting with water to form NH3 and hydronium, creating acid. And at the same time, we have our F minus reacting with water to form our HF and OH minus, which is basic. And we want to know if it's going to be more acidic or more basic. And how do we do that? Well, we have two different equations here, including acids and bases. Right? We have our first one here, which is our ammonium, and the second one, which is our fluorine. And each of these equilibriums, they have their corresponding Ka and Kb values. That's their equilibrium constant. And what we do to find the relative strength and acidity of this equation is to compare our Ka and Kb values. For our first equation, since it's acidic, we're going to be comparing the Ka. And then our second one, since it's basic, we're going to compare it to the Kb. Let's look at our first one. Ka, we look at our chart, and our Ka is going to be equal to 5.6 times 10 to the negative 10. Now for a second one. You might notice that there are no Kb values on your table, and that's because we're going to have to calculate it ourselves. So we don't have the Kb for this second equilibrium here, but what we do have is a Ka for this one. HF equilibrium with H plus and fluorine minus. And for that our Ka is going to be equal to 3.5 times 10 to the negative 4. How do we convert this Ka into our Kb? Remember that our Ka times Kb of the conjugate base is going to be equal to Kw. We're going to be using this equation. We know that Ka is 3.5 times 10 to the negative 4, not 14, 4, times our Kb, which is our unknown, is equal to Kw, which is 1.0 times 10 to the negative 14. And we solve for a Kb, which is going to be equal to 2.8 times 10 to the negative 11. Now we can compare our Ka and Kb values. Our Ka is going to be 5.6 times 10 to the negative 10, and then our Kb is 2.8 times 10 to the negative 11. Seeing this, we can see our Ka is greater than Kb. Ka greater than Kb, and because of that, we can conclude that it's going to be an acidic solution. Now for our fourth scenario, and this time we're going to be working with amphiprotic ions, such as HCO3-. What this can do is it can act as an acid or a base, and we're trying to see which one will it be more acidic or basic in water. So how do we do that? Let's write out our two equations first. So let's pretend it's going to act as an acid, okay? So as acid, it's going to be HCO3- plus H2O, CO3- plus H3O plus. Okay, now as a base, it's going to be accepting that hydrogen or that proton instead of giving it. And now we want to find out which one will occur to a greater degree. This top equation as an acid or this one as a base. And similar to our last example, we have to compare our Ka and Kb values. And we have to reference our chart here. Our first one, our Ka, if we look at it, it's going to be 5.6 times 10 to the negative 11. And our second one, we can't find a Kb, so we have to do our Kw over Ka is equal to Kb. And that's equal to 1.0 times 10 to the negative 14 over our Ka of the conjugate acid. That's going to be 4.3 times 10 to the negative 7. And this will give us 2.3 times 10 to the negative 8. Now we can compare our Ka and Kb. We can see that our Kb is greater than our Ka. That means that this solution will be basic, because our basic equation here is going to occur to a greater degree than the acidic one. And finally, if you have a salt where neither of the ions will hydrolyze, such as NaCl becoming Na plus and Cl minus, Na plus is in a Fab 4, Cl minus is a Silly 6, so they both do not hydrolyze, then you will have a neutral solution. Now let's try an example. We're asked to find the pH of a 0.15 molar NH4Cl solution. And first, we recognize that our NH4Cl is a salt. Sometimes it's not a salt, then you can't apply this, but now it is a salt, so we can apply it. So we're gonna dissociate it. NH4Cl is gonna become NH4 plus and Cl minus. We know that NH4 is a Fab 4, so it'll hydrolyze. Cl minus is a Silly 6, will not hydrolyze. Now we write our equation. NH4 plus can react with water to form ammonia and hydronium. And now using our stoichiometry ratios here, we have a 1:1:1 ratio. So I know since our original salt is 0.15 molar, our ammonium is also 0.15 molar. That means that this is 0.15 molar initially. And now we can do our ice table. Just like our previous units. Ice table, water is liquid, we can ignore that. And initially we don't have any products. We're gonna let X equal to our concentration of H3O plus. So what's gonna happen is for a change, we're gonna go minus X, and we're gonna do plus X because it's a 1:1 ratio. And we're left with this. And for our equilibrium concentration of ammonium, we're gonna assume that 0.15 is much bigger than X, so X is negligible. Say 0.15 greater than X, so we're gonna neglect X for now, so it's gonna be equal to 0.15. Now we write our equilibrium constant expression, or Ka. It's gonna equal to, it's gonna be equal to concentration of our NH3 times concentration of H3O plus over concentration of NH4 plus. And that's gonna be equal to X squared over 0.15. And looking at our chart, we can see that our Ka for this equilibrium is 5.6 times 10 to the negative 10. Doing the math, X is going to be equal to 9.1 times 10 to the negative 6. And this is equal to our concentration of hydronium. Now as for pH, so do you remember how to convert from concentration to pH? We have to do our negative log of our concentration of hydronium, and that's equal to our pH. So we have our negative log of 9.1 times 10 to the negative 6, and that will give us a pH of 5.04. Remember, 2 sig figs, so only count the decimal places. I'm going to skip over oxides and acid rain because those are a very small part of this unit. But make sure to study your acid rain stuff. I remember there was a written question on the test. Finally, let's look at how indicators work. Normally, we have an indicator with 2 different forms, and they are usually 2 different colors. Generally, our equation would look like this. We have our indicator with our proton attached to it. and it's gonna react with water. Water. It's in equilibrium with our H3O plus and our indicator without the proton. And that's because indicators are usually just weak acids or weak bases. And the acid form is going to be a different color from the basic form, which is the conjugate base. Anyways, now that we have our equation here, we can start explaining how they work. Let's say our HIN is, let's say it's red, and then our IN minus, which is the conjugate base, is going to be yellow. Now if we add an acid, we're going to be increasing concentration of H3O plus, right? Because we're adding acid. And as we know, that's going to shift our equilibrium to the left, and it will turn red. If we add a basic solution, that means we're adding OH minus, right? And our OH minus is going to neutralize our H3O plus. That means our H3O plus concentration goes down, and we have a shift to our right, and that means it will turn out to be yellow. Now when our concentration of our indicator is the same as the conjugate base concentration, that's called the transition point of the indicator. That means you're right in the middle and you're transitioning between the two colors. And what's cool about this is at the transition point, your pKa is going to be equal to your pH. And you could use this trick in different scenarios. For example, if we're told that the Ka value of an unknown indicator is 5.3 times 10 to the negative 7 at the transition point, and we're trying to find the pH, right? So what can we do? We know that this is our Ka at the transition point, and we know that at the transition point, our pKa is equal to pH. So we have to find our pKa. How do we do that? It's going to be our negative log of our Ka, which is equal to negative log of this number, which is equal to 6.28. And that's going to also equal to our pH. Easy. The last part is neutralization reactions, but that's like basically grade 11 stuff, so I'm not teaching it. It's really easy, so yeah, good luck. Okay, that's it. I'm tired. Bye-bye.